I want to start by talking about why we are using electron microscope. And I want to talk about what is ptychography, but that topic has already been covered by the previous presenters. And then I want to talk about previous near-field electron ptychography. And then I will move on to my work, which is Lorentz mode near-field electron ptychography. So as Professor Browning has mentioned, that each electron microscope costs millions of pounds to build and years of training. And even after all of that effort, it is still very hard to book your time to use one machine. So why are we bother even using them? Well, the first is that the ability to observe nanoscale material is beyond any other instruments. Second of all, we can study a broad range of specimens like biomaterial, chemical material, semiconductor, alloy metals, the list goes on. And finally, we can quantitatively understand different characteristics of the specimen, like by analyzing the X-ray ejected from the specimen, we can know which type of element is inside the object and precisely locate them. However, over the 300 years since the first visible light microscope has been invented, we are already reaching a point that perfect glass lens can be made. However, in terms of electron lens, we are not really good at making them. I'm sure we all have the experience when we are younger, we use a sunglass to focus we use a glass lens to focus the sun ray to burn down our homework. But if you remember correctly, it is always very hard to focus the sun ray to exact one point. We will always have some weird shape. That is exactly the same problem as we have in electron microscope. The electron beam will always focus at different positions, and then in the end, we will end up with a very bad shape of the electron beam as in focus position. That is why we are often in time need some post-collection image processing technology, and ptychography is one of the technology. And ptychography can give you a much higher resolution. It can also image bulk material. And since the detector of the TEM only record the intensity of the electron beam, which directly give you the modulus of the object, the phase information is lost. So a ptychography can also retrieve the phase information, as mentioned previously. And as for the near field ptychography, it can image a much larger field of view, and it can give you a much easier experiment configuration. I will quickly go over through this. Ptychography works by placing the specimen in the real space and then illuminated with a defocus probe. This probe, together with a small part of the specimen, will be propagated to the detector and forms a diffraction pattern. And then we use the same probe to scan through the entire specimen until we get a series of recorded diffraction patterns for each position. And then we move on to the reconstruction part. We started with an estimate of the specimen in the real place. It doesn't really have to be a very good guess because we have no information. It can just be a random guess. And then we have a similar process as in the collection part. And then we propagate this into the detector from the diffraction pattern. But we have the real information from the collection part, which is a real diffraction pattern. And then we use this to update both the diffraction pattern and the specimen in the real place. And then we do this over and over again until we get the full information for both objects and probe. I wonder, can I play this video? Pretty in the center, okay. All right. Sorry. Yes, we started with some random guess. The top two image are the modulus and phase information for our sample, and the bottom two images are the modulus and phase for our probe. But all four of them are a random guess at the beginning, and then as we update each position, gradually we can retry both information for object and probe. Yes, so in the end, we have Newton and Leibniz from both modulus and phase. So ptychography has been proven to be a very powerful tool. And we can get extremely high resolution. It is work done by Jiang Yi from Cornell University, and they use a twisted bilayer molybdenum disulfide. They are managed to distinguish 2 points that are merely 0.4 angstrom away from each other. And we can also combine with multi-slice to reconstruct bulk material. This is also work done from Cornell University, which is very good at doing ptychography, I guess. They can they can go as far as 30 nanometers, where most of the traditional imaging technology would already fail. And finally, we can also combine them with cryo condition and low dose, which is actually the work already shown by Alex. And even though at 100, even though at 22.8 electron per angstrom square, we are still we can still clearly image the shape of a virus. So as for the near field ptychography, it's actually pretty much the same as the conventional ptychography, but we place the detector at a position that is very close to the object. By doing this, we can image a much larger field of view, and we can have easier experiment. Because before ptychography, quantitative phase imaging has been mostly carried out by off-active holography, which is a very, very advanced technology, but it is not accessible by the most of TEM, because we do require a electrostatic biprism mounted inside the TEM, and vacuum needs to be very clean, and the specimen must be carefully aligned. However, as for the near-field ptychography, all we need to do is to illuminate the specimen with a parallel beam, and then use the selected area aperture, which is located below the objective lens, to choose the region of interest that will be propagated to the detector. Here is a video of how that will work. The green circle represents the region of interest, and the right moving image is the recorded diffraction pattern. So after we scan through the entire specimen, and then we can do the reconstruction. It is work done by my supervisor, Andy Maiden. And with this method, he can show very clear face reconstruction. However, because we require the fringe from the SAA to cover the entire diffraction pattern, this means each illumination site cannot be very large. So we take the experiment to the next level, that we use a silicon nitride phase diffuser to mask the entire illumination. By this case, we can have a much larger illumination, and then we can still do the reconstruction with very few diffraction patterns. And they can go as far as 9 diffraction patterns to reconstruct a area that is larger than 1 micrometer square. And so previous near-field electron ptychography has been able to image a large field of view with few diffraction patterns, and it can also do the quantitatively phase reconstruction. However, the phase diffuser will introduce inelastic scatters, and also the magnification is fixed due to the size of the phase diffuser. And also, we are constantly illuminating the specimen with electrons, and we are only allowing through a small region of the dose to propagate to the detector. So it's really a huge waste of the dose. So we took the experiment to another even further step, where firstly we do not use the SAA anymore, and then we move the diffuser from the SAA to the condenser length aperture. And then we also use an amplitude diffuser rather than a phase diffuser. An amplitude diffuser is a hollow design where the electrons either pass freely through the vacuum or be completely blocked by the curved edge. And then we can also have variable illumination size just by simply changing the strength of condenser length and objective length. So to demonstrate our idea, we use 3 different illumination sizes: 0.5 micron, 1 micron, and 2 micron. And then we are able to still quantitatively have phase reconstruction for a much larger field of view than traditional ptychography. And finally, we can also expand our configuration to fit Lorentz TEM, where the objective lens is turned off to preserve the intrinsic magnetic feature of the sample if there are. And we start with still non-magnetic samples because we have clear information about the parameters of the latex sphere, so we can know whether our reconstruction is correct or not. And then we move on to the exciting part, which is a magnetic sample. This is a molybdenum doped permalloy, and we also did a holography reconstruction at the same time, just to make sure that the reconstruction is correct. And I'm not really an expert of magnetic samples, so I don't really know what I'm looking at. So let's quickly, but it works, right? And finally, so conclusion, we can reconstruct a much larger field of view using near-field ptychography with fewer DP, and we can also achieve variable illumination size. Finally, we can expand our configuration to fit Lorentz TEM. I want to especially thank my collaborators, especially Penghan Lu, who carry out most of the collection part, and also my supervisor, Dr. Andy Maiden, who helped me a lot with the code, and who also pasted that picture. I forget to change that. So any questions?
Thank you for the talk. So is there any question in the room or online?
Thanks for your talk. Maybe a very naive question about the amplitude diffuser. Is this a normal DOE, diffractive optical element, or what is it exactly?
It is still, the amplitude diffuser is still consists of silicon nitride, and we basically I think it's better to show you on the design profile. So the white area are just vacuum, like the electron can pass freely through, and the black curved area are very thick, so that the electron will be completely blocked. And it's around 50 micrometer in that diameter. So I don't know whether that answers your question or.
Yes, so basically you're changing just the amplitude as you mentioned in this binary way, right?
Yes, yes, it is, yes.
Okay, and this supposed to be kind of a further step from the phase diffuser because I didn't really get.
Yes, well, because the phase diffuser is not a hollow design where the electrons will always be slowed down by the phase diffuser. So we are introducing a lot of inelastic scatters, which will further reduce the contrast in our result. Well, the amplitude diffuser, it does not cause any phase delays when electrons are passing through. So we are just using that to reduce the inelastic scatters.
Yes, thank you.
Thank you.
Maybe a following question was that the amplitude diffuser, it is known, the geometry, or you need to estimate it together with the reconstruction?
I'm sorry.
Do you know precisely the geometry of the amplitude diffuser, or you need to estimate that from the data?
We know exactly the diameter of the amplitude diffuser, which is 50 micrometer. Yes.
I think there is a question.
Okay, so we have two questions online. So one of Laura Clark. What limits the resolution on diffuser ptychography in your application?
The resolution of which result? Holography?
Ptychography.
Tychography.
Yeah, I'm sorry.
Right. So for this one, the resolution is around 3.4 nanometers. And then for the its result, the resolution changes as the variable illumination size. At best, we can get still around 3.1 nanometers, and then at worst, which is 2 micron illumination size, is around 8 or 9. And as for the magnetic reconstruction, because we are turning off the objective lens, which is the most powerful lens in the TM, so the the resolution is quite poor. As you can see previously, there are some gold particles mounted on this carbon film, and previously we can still see those small gold particles, but we can no longer see them in this reconstruction. So I don't really know the exact resolution for this one, but it's probably lower than 5 nanometer, I guess. So I don't really know for this one. Sorry.
Okay, thank you. You also have another question from Jinging Zhao. So very nice talk. Could you give some comment on the pattern you used for the condensed aperture? What do you use that specific pattern and not something else?
Okay. What do I use on what?
So for the condensed aperture, what do you use this pattern and not another one?
Okay. So the reason we are moving the diffuser from the ISCA to the condenser aperture is we want to be able to change the illumination size without changing, because previously in its design, the illumination size is limited by the physical size of the ISCA. In other words, how large we design the phase diffuser, the illumination size will always be the same. But if we move the diffuser up to the condenser lens aperture, then we can still change the strength of condenser lens and also the objective lens to have variable illumination size. And yeah.
Thank you. So we have another question here.
So as an extension to that question,
Yes.
the actual physical design of the amplitude diffuser, why was that chosen?
Oh, right.
Like,
Yes.
yeah.
Because first of all, we want the fringe from the edge to cover the entire illumination, right? So we started with some lines that are well, the line cannot be apart from each other for too large, because otherwise the fringe will not cover each other. And it cannot also not be very small, because that will block most of the electrons. And the reason they are actually curved, because we want the fringe from coming from different directions. So it has different spatial frequency. Yes.
But if you show on the next slide.
Yes. Yeah.
This one, they're mostly straight lines there as
Yeah.
well.
Actually, this is the first patch, and then we
Ah,
found out that
okay.
they are not working very well. So we come back to I come back to English again. So we did another patch and then another result.
Okay, thank you.
Thank you. Is there any other question? Yeah.
So yeah, in the last few results that you showed that you can reconstruct the phase quite accurately.
Yes.
And I was wondering, would there be any gain for your application if you would also be able to unwrap the phase? So here you're bounded by pi minus pi. Would there be an interest in unwrapping it?
Yeah. That's very nice question. Actually, that is what we are working on at the moment. I have a hidden slice just in case anyone asks me that, because when we are collecting the data, there's a construction site nearby the building. It's humping on the ground. So, and we are also moving the stage. So there's a huge drift. As a result, we are not be able to have exactly 100% match between the holography reconstruction and ptychography reconstruction. That is why you see, if I align the two results together, the green pattern is from ptychography, the pink is from holography. They are not matching each other. And then the best way to compare this difference is to unwrap them, which is the image C. And image C is actually the unwrapped and then overlapping together. So you can see we are having a constant offset, and then we are still trying to correct this. So yeah.
Okay, thank you.
Thank you. Yeah. Go ahead.
So thank you for the talk.
Thank you.
So when we talk about traditional ptychography,
Yeah.
the quality of the final phase images depending on the overlapping ratio of the probe in the case of defocus probe, right? So when we switch from there to near field ptychography, could you comment on that, like on the dependency of the quality of the phase image on the overlapping ratio? Do we gain any benefit when we switch to near field ptychography or not?
Mm-hmm. Yes, I think there is a study about how much the portion of overlap to have the best result, and I think the figure is around 30 to 70%. And then when we switch to near field electron ptychography, we have because it is quite new, so we want to have much larger overlap to guarantee the efficient information we have to the reconstruction. And so for those three results, the step size is 10% of the illumination size, which means the overlap region are 90%. So it's like over sufficient information. And no, actually, we haven't really investigated like how much portion we have to at least have to guarantee a good reconstruction, but that might be a very interesting topic in the future, I guess.
Thank you.
So these are, we would call these like low mag experiments.
Yeah.
What would need to be done or developed to take it to the, the nanometer scale? What would be necessary?
Yes. To do that, first we need a much smaller illumination probe for the sampling region, and we calculate that must be over smaller than 0.5 micron. But at that illumination size, we require a step size that is even much smaller, like 10 nanometer. But that is beyond the minimum movement stage of minimum movement of our stage, and so we have to change the scanning from the stage to the beam shift, which is currently also the next step we are going to consider. Exactly, yes, the drift.
Thank you. So I think we keep other questions for the break. So thank you for the presentation. Thanks to all the speakers of the session, and thanks to you for attending.